Welcome back. Problem 9-32. This problem is taken from chapter number 9, that is stress transformation, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the maximum in plane shear stress developed at point A on the cross section of the arm at section AA. Specify the orientation of this state of stress and indicate the result on the element at a point. So you can see this is the arm and that there is a 500 Newton load applied at point B. We have a pin support and there is a rope CD which support this arm. Clear? And we have to find at the cross section AA, the cross section of the beam is shown over here. So at this cross section, we have to find the maximum in plane shear stress at point A, and then we have to specify the orientation of this state of stress and indicate the result on the element. So let's start with the solution. So first step is that we will determine the support reaction. So if you remove this support at point B, so you will be having a reaction force in horizontal direction which will be like this. This will be Bx, clear, and on vertical direction you will be having a force which will be acting downward, that is By, and this rope acts a force in this direction which is FCD, and this FCD makes an angle of 30 degree with this arm. Clear? So we will find these support reactions this Bx and By and force in rope which is FCD by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point B is equal to 0 and taking the counterclockwise movement as positive. So you can see this is a point B, so these two forces are passing through point B. It is not producing movement, and the only force which producing movement about point B is this 500 Newton and the vertical component of this force. So this force FCD will have two component, rectangular component, one which is in this direction, this will be equal to FCD X component, and the other component is this one which is equal to FCD Y component, because you can see this will be the Y component. Clear? So this FCD Y will be equal to FCD sine of 30 degree, and this FCD X will be equal to FCD cos of 30 degree. So you can see that this FCDX is passing through point B. It is not producing any movement. So this component which is FCD sine of 30 will produce movement because the perpendicular distance is this 0.3 and it is producing counterclockwise movement. So it will be positive. The second movement about point B is this 500 and perpendicular distance is this 0.65 and it is negative, but their sum must be equal to 0. So I will write it FCD sine of 30 degree into perpendicular distance is 0.3 minus 500 into perpendicular distance is 0.65 and is equal to 0. So from here you will get this FCD will be equal to 2166.67 Newton. Now you will find this Bx by using equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So Bx is in positive direction while FCDx is in negative direction. Their sum must be equal to 0. So I will write Bx minus FCDx, which is equal to FCD into cos of 30 degree is equal to 0. So Bx minus FCD is 2166.67 into cos of 30 degree is equal to 0. So when you calculate it, you will get this Bx will be equal to 1876.39 Newton. Now you can find By by using the third equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So three forces, one is this By, other one is FCDY component, and the third one is 500. Their sum must be equal to 0. So By is downward, so minus By minus 500 is also downward, plus FCD sine of 30. So FCD is 2166.67 into sine of 30 degree is equal to 0. So from here you will get this By comes out to be 583.3 Newton. Now these are the reaction forces, and we have been asked to find the principal stresses at section AA. So for that we will cut the beam over here and we will find the internal loading at section AA. Clear? In order to get the scenario that what are the force applied at section AA. So at section AA, let me choose another color. So if you section it, so you will be having free body diagram will be like this. This will be like this. This is point B where we have Bx in horizontal direction. So Bx, we have By in downward direction, and distance between this is section AA. The distance between By and section AA is 0.15. So when you section it, you will be having a normal force acting on this face, and that will be, let this is down N, and opposite to Bx in order to keep in equilibrium, and the shear force which will be in upward direction, and you will be having a movement as well. So we'll find this N, V and M by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So By is downward, so minus 583.3 plus V is equal to 0. So it means that this shear force is 583.3 Newton. Now we have this V, we can find Bx. So for Bx we will apply equation of equilibrium, that sum of all forces along x direction must be equal to 0 and the force in this direction is taken as positive. So Bx, which is in positive direction, so Bx is 1876.39. Clear? Minus n is equal to 0, so it means that n is also equal to 1876.39 and the unit will be Newton. Now we'll find this moment by using equation of equilibrium, that sum of all moment along section AA is equal to 0 and taking the counterclockwise moment as positive. So you can see this force By into perpendicular distance is 0.5 is producing moment in counterclockwise, so it will be positive, and this moment which is producing clockwise movement and that is negative, their sum must be equal to 0. So I will write By is actually 583.3 into perpendicular distance is 0.15 minus this moment will be equal to 0. So from here you can see the moment will be equal to 87.5 Newton into meter. Now you have all these unknowns, so you can see here that due to this N compressive stress you will be have a normal stress, normal, clear, and due to this moment and due to this we'll be having a moment, and this moment will cause the beam to bend like this, clear, and the upper portion will be tensile stress, there will be tensile stress. So we will have a combination of normal stress and bending stress. In upper it will be positive and in downward it will be negative. Since this point A is above the neutral axis, so we will take it plus, and due to this shear force we will be having shear stress. So I will write it shear stress due to V, So that shear stress will be equal to, at point A it will be equal to V into QA divided by I into T, and normal stress at A is due to the compressive stress which is N by A, and that is negative because it is compressive, plus the stress due to movement which is My divided by I. The positive sign is that is the reason that due to this movement this will be bend like this, clear. So this A point lies upward, so it will be positive. Okay, so we'll find this shear stress and normal stress. So for normal stress, we need A, which is the cross sectional area, and I. So you can see this is the cross section of the beam. So A will be equal to, if you take it as a rectangle, clear. So this rectangular area will be 20 by 50. So 20 in millimeter. So in meter it is 0 0.02, and height is 50. So 50 in meter is 0 0.05 meter. So 0 0.05. This is the area of this rectangular cross section. So we will subtract the area of this two shaded portion. So this height, you can see this is 50 minus 7.5 minus 7.5, which is 35, and thickness is 7.5. Clear? So thickness 7.5, so 20 minus 7.5 will be 12.5. So the remaining, this portion is 12.5. So I will subtract it, minus 35 millimeter, which is 0 0.035 meter, into the remaining was 12.5. So 12.5 is 0 0.125 meter. So when you calculate it, you will get the area of I beam, which comes out to be 0 0.5625 into 10 raised to power minus 3, and unit will be square meter. Now we'll find I, which is the moment of inertia, and moment of inertia for this symmetrical I beam about the half will be, or its neutral axis will passing through centroid, because this is symmetrical there. So it will be equal to 1 over 12 B, which is 20. So 20 in meter is 0 0.02, and height is 50 millimeter, which is 0 0.05 cube, 1 over 12 BH cube, minus the moment of inertia of this remaining two portion. So this height was 35 millimeter, which is 0 0.035, and the remaining two portion is this one. Clear? So minus 1 over 12, breadth is 0 0.0125, and height is 0 0.035 meter, and it will be cube. So when you solve this, you will get the moment of inertia comes out to be 0 0.16367 into 10 raised to power minus 6 cubic meter. Now you have A and I, so you can put in this formula. N is minus 1876.39 divided by area is 0 0.5625 into 10 raised to power minus 3, plus movement is 87.5 into y. Y is distance from neutral axis till point A. Y, this is YA, and this YA is equal to, this total distance is 35. So 35 divided by 2 is 17.5 millimeter. In term of meter, it will be equal to 0 0.0175 divided by I, and that I is 0 0.16367 into 10 raised to power minus 6. And when you solve this, you will get the normal stress due to this two stresses will be equal to 6.020 megapascal. Now we will calculate shear stress, and we know that shear stress at point A is V into QA divided by I into T. So what will be V? V is this one, and QA is equal to Y dash bar into A. So A is this area which is above the point A. This is your A, and this A is 7.5 millimeter thickness, and width is 20 millimeter. So I will write the value of A, 7.5, which is 0 0.0075, clear, into its width, which is 0 0.02 meter. And what will be the Y? So Y dash bar is distance from neutral axis till the mid of this section, and this distance is Y dash bar, and that is 21.25 millimeter. Because this distance is 17.5, you can see, and 7.5 divided by 2 will be this distance. So when you add it, it will be 21.25. So So I will write 21.25 is 0.02125. That will give you QA. And when you solve this, you will get QA will be equal to 3.1875 into 10 raised to the power minus 6. So put it in this formula. Shear stress at point A is V. So V is 583.3 into QA is 3.1875 into 10 raised to the power minus 6 divided by I. I is 0.16367 into 10 raised to the power minus 6 and T. So T at point A is, you can see this is 7.5 millimeter, which is 0.0075 meter. So when you solve this, you will get the shearing stress at point A comes out to be 1.515 megapascal. Now if you draw it on element, so this is the element. So normal stress at point A, which is sigma x, is this one in x direction. This is sigma A, or you can also write it sigma x. So this is sigma x, and there is no sigma y because there is no stress in y direction, and shear stress will be like this. This is tau of xy, or that is tau of A. This is tau of xy. Clear? Now this problem is ready to solve. Our first part, determine the in-plane shear stress. So for that, I will copy all this data and we will move toward our second page. Let me copy it first. I'm going to copy it and we will move toward next page. Here I will paste it and resize it so that we can see the. Now focus over here that you can see on this element. Here we have sigma x is equal to 6.020 megapascal. Clear? Sigma y is not available, so it will be 0, and tau of xy is 1.515 megapascal. In part first, we have been asked to determine the maximum in-plane shear stress. So maximum in-plane shear stress at point A. So we know that maximum in-plane shear stress is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy square under the root. So put the value 6.020 minus 0 divided by 2 whole square plus tau of xy is 1.151 square under the root. And when you solve this, you will get maximum in-plane shear stress comes out to be 3.37 megapascal. So this is the answer of our first part. Now we will move towards second part, and in second part we have been asked to specify the location orientation. Specify orientation of this maximum in-plane shearing stress. So we know that maximum orientation of in-plane maximum shear stress can be represented by this formula. Tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2 divided by tau of x y. So put the value minus 6.020 minus 0 divided by 2 divided by tau of xy, which is 1.515. That will give you tangent of 2 theta s. So tangent of 2 theta s will be equal to minus 1.9871. And this 2 theta s will be equal to tangent inverse minus 1.9871, and you will get this 2 theta s will be equal to minus 63.29 degree, or theta s will be equal to minus 31.6 degree. And there is another plane which is theta S2. This will be theta S1 and theta S2 will be equal to 58.4 degree. I will show you in a while how we will get this. Now we have theta one plane at angle of minus 31. Minus 31 means this angle is, the element rotates 31.6 degree clockwise, and the theta S2 is either it should rotate 58.4 in counterclockwise. So we want to check it. So put theta is equal to minus theta S1 is equal to minus 31.6 in shear stress transformation equation, which is tau of x dash y dash is minus sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy cos of 2 theta. So let me put it. Tau of x dash y dash will be equal to minus 6.020 minus 0 divided by 2 into sine of minus 63.29 plus tau of xy, which is 1.15 into cos of minus 63.29 and degree. And when you calculate it, you will get this tau is 3.37 megapascal, which is the same maximum in plane shear stress. But we have confirmed that if you draw the element, let this is the initial axis x and this is y, clear? And when you rotate it through angle of minus 31, so minus means clockwise, so this will be, let this is your new x dash and this theta is your theta S1 is 31.6 in clockwise direction. So your y new y dash or transform axis y dash will be this one, and if you draw the element like this, so this will be the element, and you can see that tau of x dash y is positive, so it should be in upward direction. This is in y direction, positive y dash direction. So this is tau of x dash y dash, our maximum in plane shear stress, clear? So we have represented on element. So with this we have also average normal stress. So average normal stress, and we will also represent it. Average normal stress is equal to sigma x plus sigma y divided by 2. So 6.020 plus 0 divided by 2 will give you average. So average normal stress comes out to 3.01 megapascal. And if you want to represent this is positive, so it means that this should be in positive direction. This is average normal stress. So these are the answer of our second part, and this representation which is indicate it on element, clear? And this is the answer of our third part, clear? And you can see that this is the angle 31.6, either to rotate it in clockwise direction or this is anti-clockwise direction. This is theta 2s, which you can see that if you subtract 90 degree minus 31.6, so it will be equal to 58.4 degree, clear? So in that direction you can see you will also have a shear stress, transform shear stress or maximum in plane shear stress. And that was all about this problem 9-32. I hope you have enjoyed this video and you are learning as well. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.